Hello everyone, welcome to this video. In this video we shall see another property relating to compact linear operators. So here we are going to talk about the null space of compact linear operator. So without wasting much time, let's move on to the lemma. So the lemma here states that whenever we have some compact linear operator, so this thing is given to us, right? And we define the operator by t from the normed space X to the same normed space, where again lambda is non-zero complex number. Then they are saying there exists a smallest integer r which depends on lambda, such that from the index n onwards the null spaces for the operator t lambda power n are all equal, and if this r is greater than 0, we have the inclusions which are all proper. So all of these inclusions, they are proper. So first of all, let's understand what this lemma is trying to say to us. So you are given just a operator t from the normed space X to the normed space X, right, to the same normed space. So here, corresponding to this operator t, first of all we are defining t lambda corresponding to a fixed lambda. That means whenever we are keeping this lambda as fixed, so we are keeping t lambda as fixed corresponding to that complex number lambda. So we can define this to be t minus lambda times the identity operator, right? So now we could have t lambda 0 power 0 means we are talking about the identity operator. T lambda power 1, that means we are talking about t lambda. Then t lambda power 2, so that means we are talking about t lambda square, and so on. We can increase the power of this operator, and how do we obtain that? By composing the operator. So now relating to t lambda 0, t lambda raised to power 1, t lambda raised to power 2, t lambda raised to power 3, and moving on like this. Now we are talking about the null space of each of these operators, right? And what is the relationship among all of these all of these null spaces? So according to this lemma, they are saying there would be some index here, the power here as r. So basically I am saying the null space of t lambda raised to power r. So from this index onwards, from this r onwards, we are saying all the null spaces from this one onwards, all the null spaces, they are equal to each other, and moreover these first null spaces, they are contained in each other, with the first one being the smallest, right? So here, in order to prove this, what do we have to do? We have to first show that there is some index like this, n is equal to r, such that all the null spaces before it, they are all proper inclusions, and after it are all equal. And next thing we have to say that, so let's just formalize this one. So here just see, if we define the notation of the null space for the operator t lambda raised to power n as capital N subscript small n. So this is the notation that we are defining and using in the proof. Using this notation, we are proving the result as that we assume that the null space nm is equal to the null space nm plus 1. So basically what we are saying, n of t lambda raised to power m, that is equal to n of t lambda raised to power m plus 1. So we assume that this thing is not true for any m. That means there is no such m such that this thing is true. We assume this thing, that means we are assuming the opposite, because we wanted a number such that after that all the null spaces become equal. So we are assuming the opposite. So when we assume the opposite in the process of the proof, we reach at a point which gives us a contradiction to some of the assumptions stated in the lemma, and the proof could be done in that case. And next we tell so in the first part we would say that there is such index m such that all both of the null spaces, they are equal to each other. And in the second part we will prove that from that index onwards all the null spaces, they are equal to each other. So that means if we assume that n of m is equal to n of m plus 1, so for all the indexes which are greater than that of that particular index m, the null spaces, they are equal to each other. So this is what we are going to prove here in this lemma. So let's see the proof. For first part, what we have to, we first of all we assume that for no m, n of m is equal to n of m plus 1. So that means we are saying both of them, they are not equal to each other for the index m. But however, we know that null spaces of compact linear operator, they are finite dimensional, and moreover each of these null spaces, they are contained in each other. So we have the containment, and that is clearly well defined, right? We know each of these null spaces, they are contained in each other. So what we are required to do here, we have to say that in this chain of inclusion there is some null space here, null space t lambda raised to power r, such that after this index all of them are equal. So first of all we will say that after this the next one is equal to this one only, like something like that. So for this we are proceeding through the process of contradiction. So what we are saying is that we are saying that for no m, so here the index, I am not taking r but I am taking the index as m. So we are saying for the index m, the null space nm, that is equal to the null space of nm plus 1. That, so both of them are equal for no m, right? In that case, n of n is a proper subspace of n of m plus 1 for every n, right? So that means if they are not equal to each other, then one would be proper subspace of other. And moreover, we know from the previous results that the null spaces, they are closed, right? Because the null spaces of a compact linear operator, they are closed. So we can apply Rie's lemma here. And according to Rie's lemma, if you remember, if we have subspaces of a normed space X denoted by Y and Z, and if one of the subspace Y is closed and moreover it is a proper subset of another subspace, then there would exist some real number theta between the interval 0 to 1 such that we take Z from the upper subspace, right? The bigger subspace, and whose norm has to be equal to 1, and moreover the distance of this particular Z from some member of Y has to be greater than that particular theta which we choose from the interval 0 to 1. So in this case we would say that because all the null spaces, they are closed, so therefore we would take now I would say n of n minus 1 is contained in n of n, and both of them, they are closed, right? So what we are saying, we are taking some number from here, calling it by yn. So the norm of this yn is equal to 1, and the distance of this yn with some member here of this null space and n minus 1 is greater than equal to some number lying between the open interval 0 to 1. So I am taking that theta to be equal to 1 by 2, right? So this is how I am applying the Rie's lemma here onto our null spaces, right? So we have this property here on the null spaces. Now in order to prove that for no m, in order to make the contradiction valid, so what we have to show, we will show that the norm of Tyn minus Tym is greater than equal to 1 by 2 times of the modulus of the given complex number lambda. So remember that this lambda here is fixed, and because we are keeping this as fixed, so that is why all these operators T lambdas, they are defined, right? Okay, so now we will show that this thing is true. Now why we are doing this? Because we know that T is given to be a compact linear operator, and because if we prove that the norm of t by n minus t by m is greater than equal to half times the modulus of lambda. So that means this sequence t of yn, so this sequence would not be convergent according to this condition, right? So that means this would have no convergent subsequence because this quantity modulus of lambda is always positive in nature. If this is positive, so this is going to be always a positive number. So this the norm is going to be greater than this positive number. So we would say the sequence here t by n has no convergent subsequence. So if that is the case, and because the sequence yn is bounded, so therefore why it is bounded? Because here the norm of this yn is equal to 1. So this is a bounded sequence, and moreover t is compact. So when we apply t onto this yn, that should contain a convergent subsequence according to the convergence compactness criteria. But if this thing happens, so it would fail this compactness criteria according to the operator t, and we would reach at a contradiction. So we have to prove this thing here. So in order to prove this thing, we take the difference of these two operators tyn minus tym. For that, if you remember, what was our t lambda? It was t minus lambda I. So from here I can extract this t. So our t would be t lambda plus lambda I. So accordingly, this t could be written as t lambda plus lambda I, and again here this t could also be written as t lambda plus lambda I. So I have clubbed these terms and I am writing this term here, and all other terms I am clubbing as x tilde, right? So what I am left with, t of yn minus t of ym, that is equal to lambda yn minus x tilde. So basically, in order to prove the result, I have to prove that the norm of tyn minus tym, that is equal to the norm of lambda yn minus x tilde, and I have to prove this thing is greater than equal to 1 by 2 times of modulus of lambda. This is what we have to prove. Okay, now in order to prove this thing, the second part of this thing, so what do? We consider that the index m is less than the index n, and we show that this x tilde is present in the null space n minus 1. Now because this index m is less than n, so that means m has to be less than or equal to n minus 1. That is quite obvious. And if this index m is less than equal to n minus 1, so in that case ym, which is a member of nm, when multiplied with lambda, there is no issue, right? So lambda ym is a member of mm, that is no issue, and this nm is contained in n minus 1. Why? Because m is less than equal to n minus 1 here. So this is one term. So we have lambda ym contained in n of n minus 1. One thing. Another thing, we know ym would be there in nm, right? So when we apply the definition here, so t lambda of m, when applied onto ym, that would be equal to 0. So this is what we have written here, and I can write t lambda m as t lambda m minus 1 times or composed with t lambda of ym. So whole of this thing is equal to 0. If this is equal to 0, that means whole of this thing is present in the null space of m minus 1, right? So t lambda ym is contained in the null space of m minus 1, and because m is smaller than n, so m minus 1 is strictly less than n minus 1. So from here n of m minus 1 is contained in n of n minus 1. So from here we have t lambda ym contained in n minus 1. So this is the second result. So we have this one thing, we have this second thing, right? And let's see the third thing also. For the third thing, we again know yn would be contained in nn, no issue, right? So what does that mean? It means that t lambda of n applied onto yn is equal to 0. So from here you could see t lambda of n minus 1 applied onto t lambda of yn, that is equal to 0. So that means this thing would be there, t lambda of yn would be there in the null space of n minus 1. So that is what we are writing, that t lambda of yn is contained in the null space of n minus 1. So this is the third thing. So we are saying this term is contained in n minus 1, this term is contained in n minus 1, and the first thing, lambda ym, is contained in n minus 1. And let's have a look at the definition for x tilde. It is composed of these three terms, right? So that means because all of these three terms are present in n minus 1, so this x tilde is present in n minus 1. If that is the case, so in that case, lambda inverse x tilde is contained in n minus 1. So this x tilde is contained in n minus 1. So if we write x as lambda inverse of x tilde, that is also present in, that will also be present in n minus 1, right? Now, because we wanted to prove that the norm of lambda yn minus x tilde is greater than equal to 1 by 2 of modulus of lambda, so let's look at this term. So let's take this modulus here, the norm here of this quantity. So this lambda yn is as such, and x tilde now could be written as lambda times of x. So that is what I have written. So because lambda is there, so by simple algebraic calculation you could take out this lambda here, the modulus of lambda outside. So we are left with the norm of yn minus x, and from the equation above, let's have a look. From the Rees lemma here, we have developed that the norm of yn minus x is greater than equal to 1 by 2, where x was some member of n minus 1. So this is also the case in this case also. So here also this x is some member of n minus 1. So we can we obtained this inequality here. So the norm of ty_n minus ty_m, which is nothing but the norm of lambda yn minus x tilde, that is greater than equal to 1 by 2 times of modulus of lambda. So this proves equation 2 here, and because t is given to be a compact linear operator and yn is bounded sequence, so this result gives a contradiction to the compactness of the operator t, and hence we reach at a contradiction. So whatever we have assumed in part A, which states that nm is equal to nm plus 1 for no m, is not correct. So that means it has to be true for some m. So this proves that we have a equality at some point of time, at some index. Next we will prove that from that index onwards, all of the null spaces, they are equal to each other. So what we wanted to prove? We wanted to prove that if m is the first index from which we have the equality, so that means n of m is equal to n of m plus 1. So, and for the index which are greater than that particular m, all of the null spaces, they are equal to each other. We wanted to prove this thing. So we start with the by taking the we start a proof by the method of contradiction. So we assume the opposite. We assume that this thing does not hold. So that means we assume n of m is equal to n of m plus 1, but for every n greater than m, both of them, n of n is not equal to n of n plus 1, right? So if they are not equal, so that means we would have this n of n as a proper subspace of n of n plus 1, right, for some n greater than m. So in that case, because we are saying that is a proper subspace of n plus 1, so in that case, if we take the difference, that difference should be non-zero. It should contain at least one element. So we call that one element as x. So this x is contained in the difference. So that means this x would be there in n plus 1, but this x would not be there in n. So if this x is there in the null space of n plus 1, so what does that mean? It means t lambda of n plus 1 applied onto x is equal to 0, and according to this definition we have this thing. So let us mark this as equation number 5. Now we know the index n is greater than m here, so therefore n minus m is a positive quantity. So let's take t lambda of n minus m times x as z. So we are setting this thing. You'll see why. So that when you apply t lambda of m plus 1 onto this z, so let's see what do you have. Just substitute the value here of z. Perform some calculation. So you see you have t lambda of n plus 1 times x, that is equal to 0. So you obtain t lambda of m plus 1 z is equal to 0. Why this is 0? Because by making use of this equation 5 here, right? And similarly, when you apply t lambda m onto z, so substitute the value of z here, perform the calculation. So you see t lambda n raised to power n applied onto x is not equal to 0, again using the equation 5 here, right? So now here we are saying t lambda of n plus 1 x, here we are saying, just have a look, we are saying t lambda of m plus 1 z is equal to 0 and t lambda of raised to power m of z is not equal to 0. So this means that z is contained in n m plus 1, but it is not contained in n of m. However, in the very starting, we have assumed that n of m is equal to n of m plus 1. But here we have proved that n of m is contained in n of m plus 1. So this is a contradiction because we have assumed this thing for m, and hence whatever was our assumption, that is incorrect. So therefore whenever n of m is equal to n of m plus 1 and we have some index which is greater than this m, so for that particular index n of n is equal to n of n plus 1. So this proves that whenever we have r as this smallest integer such that all the so that means there exists some smallest integer r such that all the null spaces are all equal whenever we have n equal to r, and before r we have all the inclusions, and after this r all the null spaces they are equal to each other. So we would say in the chain of this null spaces we have proper inclusions up to the index r, and after this index r, where r is the smallest integer, where we have the equality, and after this integer r we have all the equalities. Before this we have all the proper inclusions and so on, right? So this is the lemma which gives us a very well defined result on the null spaces for a compact linear operator when a complex number lambda has been fixed to it. So I hope you understood this lemma and it proves well. I'll see you next time.